Hello, welcome to this presentation. I'm Gérard Borrello from Interac, and I have posted a few days ago a presentation on the physics of double glazing system. And this video now is intended to show how easy it is to create such a model in C+ software. So for the physics, we were comparing transmission loss for measurement with transmission loss for model, and perturb, in fact, this model in different way, including also triple glazing modeling, in order to see if we reasonably can approach test result with statistical energy analysis modeling. And the answer was yes, it was pretty good modeling from a statistical C model. And we also show that there is error not to be done when doing such a model. And in that case, I will show you the new functionality to help you to create such a model in a quick way with more safety. So we have opened a page in C++ page. So this is, I opened the file I've used for my last letter presentation. And I will just create a new page model. Here, I just create new SCM model. Okay, new page. Increase a bit the window size. And in that page, we will start just by creating our double glazing model. And we need some data, but we will interact a little bit the data from here. And in the local menu, so I will select a little bit higher to see the model completely. With the local menu, we have add subsystem, this new function double wall here. We call it directly from here. So you have the dialog box, which will create directly this model where it is cross-coupling ring loss factor. So you have typically for the double wall glazing cavity, emitter cavity, where is the source, acoustic source, assumed to be diffuse. This cavity is loading by pressure the first plate, which will be our 4mm plate. Then you you radiate in a fluid gap, 10-12mm, and then you will load the third plate, the second plate, which will be 10mm thick in glass material, and then this final plate will radiate back in the receiver cavity. Alors, I started by cavity modeling from bottom to top. So the data I will feed is 80 square meter for the cavity, 48 cube meter, and 44 for the perimeter. Just the same data for the receiver cavity, 88, 80, identical in size, but you can put something else. But as soon as the cavity is large enough, there is not much effect of cavity model density on the transmission loss. This is not a major issue. So the panel is relatively small, 1.48 times 1.3. 1.23. This is the size of the double glazing, the glazing itself. And here, to get the data, you have two options. Either use an option in the database that have been already created. Either just using this shortcut to create a new set of material, another shortcut for the material. And in that case, we will call it glass, call it my glass nut. And here the classical value, this is relatively stiff Young modulus, but it has been given by my customer, the data of the Young modulus. For this particular panel, we will put 500, not its exact value of the aluminium in that case. And we just, I think it's 0.22 and compute the shear from the Poisson ratio. And the damping for the moment we let to 1%, constant damping, internal damping, material damping. And then my uniform section will be my glass 4 millimeter, and glass correctly written. Okay, that's okay. And the thickness 4 millimeter. So I create my material, all right, and then I have my section and material here, where we can verify afterwards. In that case, we have to insert a trim into these two panels, because we can make different kind of model than a simple double glazing system. So we can more generally put a trim with any kind number of layers in between. But in that case, we just edit this one and save under a different name, which we call air gap 12 millimeter, okay, in air. So I remove the current layer and put air gap, fluid gap here with this name. Call it my air gap to be sure. And thickness 12 millimeter. Right, this is the model. And there is fluid additional absorption, generally difficult to measure, but we have put a parametric spectrum. Per default is 1%, but we can play with it in the database, so it's avoid changing the spectrum when we want to make parametric study on air gap damping. Okay, and that's nice, air. This is a parameter per default that are used for computing the transfer matrix of the air gap. I will not go in the detail of calculation here. It's the loop of frequency you set, because it's assuming a diffuse field excitation. Second material is air gap 10 millimeter. Okay, glass, uniform glass 10 millimeter already in the database, and with the same 1.48, 1.23 dimension. Just verifying all my data. Simply supported. Modal interpolation. Modal interpolation means we will locate, in fact, the mode at low frequency, making clearly visible with an interpolation function based on the mobility expression of the material. And then we can click OK. And then the model is done. If we look at the way it's done, the physics, you have the emitter cavity, and the two panels, and each panel has a trim, which is the rest of the double wall system. So for the panel 4 millimeter, you have the thick panel 10 millimeter connected by a fluid gap 12 millimeter. And in terms of physics, you see the cavity is radiating to this coefficient, to this coupling loss factor. It's exciting the mode of the panel, in that case through the radiation efficiency. And if you look at the radiation efficiency, we see the radiation efficiency of the 4 millimeter panel, which is have a peak at 3 kilohertz, this peak being related to the critical frequency of the panel. When you select the wave number, you see that at 3 kilohertz, the wave number intersect, because they have not the same slope. The acoustic wave number is omega over c, so the wavelengths wavelength is the invert of it, so it c speed of sound divided by f frequency, and it's constant. The speed of sound is constant with frequency. That means the wave number is growing as frequency. So 6 dB slope in a log scale, while the structural wave number is a flexural wave number proportional to the square root of frequency. And then is only have a 3 dB slope, so they intersect at some frequency where the structural wavelengths and the acoustic wavelengths are the same. That means a transfer of impedance which is maximum at this frequency. So it's why we have this big peak. If I Control G to plot display the radiation efficiency, and very low at low frequency, because only a fraction of the mode is radiating at low frequency, corner mode, and as Majdanek theory is stating. And then in this region we will see that it's not the resonant behavior that is dominant due to the weakness of the radiation loss factor. We close all other curve. And so the panel mode then are radiated in the second panel through this, which is a mechanical coupling loss factor, because we assume these two plates are maintained by a frame, metallic frame, small one, and this metallic frame induce line coupling on the panel, which is per default equal at the largest dimension, but it's something that has to be set up correctly. So as the default value, because if not, the dialog box will be too long to create, and it's easy to change afterwards when the model is creating. So the second panel is trim, but is indirectly excited by the cavity, because the acoustic energy have to cross this panel first before reaching this, and this panel has a trim, okay, which is the other panel, plus the air gap. And finally, the mode of this panel are radiating in the emitter cavity through the radiation efficiency, and you will see in that case the radiation efficiency is at a lower frequency because it's a thicker plate. A thicker plate means that the wave number is slightly different, offsetted down, it's lower. So then when you look at the wave number, you see the critical frequency is dropping down with the flexural wave number, intersection with the acoustic wave number. And so this explains this peak in radiation efficiency, which is automatically converted by the code into coupling loss factor, which is a fraction of energy that going from the panel to the cavity in that case, to the other coupled subsystem. And the reverse, because the power flow is bidirectional. If this panel can send energy to the cavity can send back energy to the panel. And there is a reciprocity in between these two coefficients that is equal to the ratio of the number of modes. So, and because cavity has a lot of mode, so the energy per mode of the receiver cavity is very low, and then this increases the gap between the coupling loss factor at high frequency. Then we have also this extra coupling loss factor that are interpreted as mass low coupling loss factor. If you double click on them, you will see that this is computed from transfer matrix approach, because each time we connect a trim on a panel, we have some option, which is added mass, added damping, but also if we do that, compute insertion loss, that is a difference between with and without the first panel. And so this insertion loss is given by, and as well as mass flow correction and mass correction and damping correction is computed from the transfer matrix approach, which is the second, the CIF, handled by the CIFOM calculation module, internal to an internal library to C++. And then we have a strong coupling between, in fact, the transfer matrix approach and the SEA approach. So the SEA provide, in fact, all the parameters of resonance system, such as mode in band, the two mode in band. Here we are in the third octave band. Up to calculation is pushed up to 10 kilohertz. So the first mode is the lightest panel, which is a panel 4 millimeter, with mode but around 15 hertz, something like this, simply supported. And what you see is that when you couple by the transfer matrix approach the mass of the plate, you see that we have an increase of mass. At low frequency, you have one mass, the mass of the total assembly. It's in fact everything is moving in phase. So there is only one large subsystem at low frequency around the first mode, and the spring the fluid that acts as a spring between the two panels. So you have at some frequency, a brazing frequency in this region. So the mass is increased because it stops the vibration, and the energy is stored locally. So you have a drop in the transmission, and then the mass is decreasing afterwards because the two plates are acting as weak coupled subsystems, so they are behaving as individual free subsystem, I would say. So physics is a bit complex, as you noticed, and you have this connection factor, coupling loss factor, that depends on the way you couple mechanically the two plates. In that case, we have assumed a line junction about some length. And then we get this problem. So what I will do is to first add some source. Here I will add a source of constraint. Unit pressure I put in my cavity just to verify I can connect sources, okay? And then I just solve it. Here you have a button for solve model. So it does the job, and then I can verify I have velocity and acoustic pressure in my system, so selected subsystem, engineering unit, and then I have so two plots, one for pressure, unit pressure, transmitted pressure, attenuated by the trim, and the acceleration or velocity, if you like. Engineering unit is plotting default RMS acceleration, 10 to the minus 2 up to 0.1 meter per second RMS on the structure. All right, but about transmission loss, we can then compute adimensional transmission loss from this button. So we just click here, emitter cavity, receiver cavity. Because there is no direct plate coupling between the two cavities, you have two separated plates. We have to fix up the size from this list. In fact, the final they have all the same size for the panel, so we have no problem. The size of one panel is the size of the transmission loss area, and then I compute the transmission loss, okay, directly from my model. Default model in that case. Then I get this result, and what I'm doing now is to compare with the test result I have stored in the database. So I've imported through Excel using import function. You have, when can create a new transmission loss coefficient, you have import here, and you can import a text format or copy and paste and this kind of stuff. In that case, it's already done, and my customer measurement are here. In fact. So third octave from the measurement, which lie between 100 and 5 kilohertz. And then when I Control G, I call for my graphs. In fact, I can drag and drop the test result just on my default prediction, and we see there is some discrepancy, but the trends are here. A big dip in the transmission loss due to brazing frequency, which is not so much important. Then 18 dB slope increase, as we know from double glazing, and then after here it's some mechanical links that dominating the pass, and here we had bigger dips than what is expected, and looking at what's going on in the model, we can go back to the model and ask for different plot. The first plot is where is coming the energy when I solve it, so I have to solve, and graph. I look at power inflow in the subsystem to see what is the most important sources. So there is the sum of all paths entering in the cavity. So I disconnect the total power input. It is the sum of all power input, and I see following frequency 2 main paths. This path, which is in fact coming from the emitter cavity. So this is this direct path here, which is a mass flow connection between the two cavities, and this is dominating up to 1000 Hertz. About 1000 Hertz, above 1000 Hertz, in fact, is the energy coming from plate 3. Plate 3 is this plate, the plate on the receiver side. And so what we need now is to know where the energy is coming in plate 3. So I use a power flow input in plate 3. And in plate 3, I think this is the main path. It's coming from plate 1 in the up to 2 kilohertz, plate 1. And below, it's coming from here. And here it's coming from the receiver cavity. So it's a re-radiation of the cavity in the receiver. So in fact, most of the energy is coming from plate 1. In fact, what it means there is looping. In fact, in this model, you have non-resonant energy going in cavity, and at high frequency, this non-resonant energy in the cavity is radiating back into the receiver plate. That's a fairly complicated path. And then if we get a look using a power flow plot, we can put some frequency. Also, we can observe for example, in the 500 range, mid-frequency, what is going with some dynamic range from 30 dB, for example. Obviously, I have to move a bit the plate apart to see what it does. You see there is effectively what is coming inside within 20 dB is the energy directly seen from this cavity, and the energy radiated by the coupling is neglectable. If you want to see it, you have to increase the dynamic range, and the scale of the arrow is automatically about maximum power flow. And you see that this is a predominant power flow at 500 Hertz. Secondary paths are the radiation by plate. So if we go to up higher frequency, 2 kilohertz, of course, it's different paths. the most important pass is coming from the radiation of the plate, and for the receiver cavity, is the receiver plate. In fact, that is the mode of the receiver plate directly radiating, and the mode of this receiver plate, if you reduce the dynamic, is mainly coming at 2 kHz from the first plate. So definitively, you have this pass at high frequency, that is the second pass, primary pass at 2 kHz. And if I go to 10 kHz, still the case, in fact, all other passes are eliminated. And then you see the main pass quickly. So you have, in this problem, two main pass, direct non-resonant pass for the two cavity, and mechanical pass at high frequency that has to be scaled against the mechanical coupling loss factor between the two plates. So that, now if I move back my structure at the same location, this magic button to put everything in order. Then we see that now we can improve a bit our correlation. What I've done for my last presentation is to improve the coupling loss factor. So what I've done is assuming, because there is a frame all around the window, that means in fact I just use a periodic junction with a periodicity of 1.23 because there is a distance of 1.23 between the two junctions. And I put this infinite coupling function here, and I need to add a second coupling loss factor because in the other direction the two other edges are connected, and in fact they are phased somewhere. So I connect subsystem. Connect the subsystem, so 0 degree, which means the two panels are top of each other. Infinite coupling means I don't consider that the second subsystem has some feedback, and 1.48 here, but I use periodic junction. Also here I use 1.23 with a periodic junction 1.48 between the plate. So let's go what it gives. I have two different mechanical junctions. So this one port 48, so the two lines are spaced by 123. So there is some correlation between the two junctions that is taken into account by this periodic junction click about two junctions being separated by 1.23 meter. And in the perpendicular direction, you have 123 lengths one direction with two junctions being separated by 1.48 meter, and that gives slightly different results. So if I compute the transmission loss from this compared to previous, and what it gives, just remove some of the graph. We use, okay, just drag and drop that third one. You see very, very low difference. So our default model could be considered as rather good. This is not a major issue regarding the quality of computation. What change to what coefficient? So I just what are the effect of if I look back to my transmission loss, I have not so good result I'm making my presentation, simply because now I will just modify the damping loss factor of my panel. I will use something scale-on measurement. And here I use this damping loss factor proportional to 1 of the square root of frequency. So decreasing measure coupling loss factor for the flexural wave. For the other wave, I don't really bother. But in that case, because it's scale-from measurement, I need to disable the combined effect of the modification of the damping loss factor by the trim. So in that case, I end it in damping at the enable. Well, we will just, and if I look at the damping here, you will see damping loss factor. You see that decreasing damping loss factor. And now I can solve back the transmission loss again to see if it does make any change to my system. 1.82. And selecting now the 2 and 1.04. Okay, you need to first select cavity after to answer the surface, and okay, this result. And now if I compare to previous, just go back here, up, clean up a bit everything, because it's rapidly, we get crowdy, and then I will just draw back, and then, you know, this is the last result, a bit better at high frequency. Huh? So you see that the level at high frequency is really controlled by damping. At low frequency, it's a bit too low, in fact. Huh? So our transmission loss is too low. That means there is too much transmission in the system. And what I've discovered, very simple consideration about modal excitability, is in the case where, in fact, where I have highly radiated cavity, and this may be demonstrated using energy model, deterministic energy model based, for example, on variational principle, in order to check all the theoretical of the theory of the transfer between structure and a cavity, small cavity. In that case, in fact, the cavity around the brazing frequency, there is air compressibility, and there is modal selectivity, because this cavity acts as a special filter for the structural mode transmission. That means all modes which are even, that mean even mean a number of half wavelengths inside the mode shape. This mode have no volume variation, so they cannot participate to the stiffness of the air gap. And then, because they don't participate, they have no transmission. And then only half of the mode are the uneven mode, odd mode. The odd mode can only transmit their energy in between. So that means this pass, which is the non-resonant pass, which is dominant, need to be corrected by a factor of 0.5. To have this correction, you just go to the database, and you may add any transfer coefficient, a new transfer 0.5 formula. You have a formula, you can write a relatively complex formula here, and a simple one, in that case, constant value, and then you get this coefficient, 0.5, and then you can, of course, using this transfer, do the same things as this one, which has already been created, 0.5. In that case, I put 0.5 here, which is to say, okay, the total number of modes that contribute to the transmission is only half of the number of physical modes. Of course, I could also correct other coupling loss factor, but it's mainly acoustic transfer through the acoustic transfer through the air gap, which is predominant, and it is condensed in this dominant path. So it's not necessary to think about the other coupling. And in that case, if now I recompute the transmission loss with this additional correction, sorry, I need up, and then type in the number. Okay, I have this result. Not much different, but if I look back with the previous, you see that the correlation between the tests now is really much more better. That means little by little we have improved the correlation with tests. No, I think that one, not that one. Okay, this is a 2. Of course, you have still a bit of deviation, but obviously this is due to the fact the problem is not exactly solved by a transfer matrix approach because it's infinite medium, and then the breathing frequency is scattered around a lot of frequency, and generally we have an increase of transmission loss just before here. But on first, with some default value, just a tuning of the damping, and in fact the tuning of the damping maybe relax a bit, because if you say, okay, I don't know about the damping, so I will rely on my transmission loss computation, so I put 1% back. In fact, 1%, I think 3% should be a better guess. Huh? A better guess, so if we put 3%, which is the mean of the measurement using impact hammer, if I enable again the correction, yeah, the damping add correction, so the trim modification of the damping loss factor of the system, damping from trim, then I can solve again, Control G. And is it too different from, so we have to compute the transmission loss, huh? Up 1.8204, and then I have this result, Control G, and if I compare to my best prediction, you see it's similar. So that means even if you use this one, the default damping, as soon you have an approximatively constant value over the mid-frequency, which is 3%, here you have a nice prediction, because the damping is not so much effective. And your final damping which is used is that one, in fact, in that case. And if I compare to my initial damping I put in the database, so we just put the damping on the database. That one, Control G. If I compare, you see, in fact, it's mimicking the true damping, in fact, at least above 800 Hertz. Below you have a difference, but as we are not much controlled by damping at low frequency, you have a correct answer regarding your sound transmission loss. You see that you don't have to really puzzle about modeling double glazing. It works. Residual error are mainly due to damping, exact damping, or junction modeling. We don't know exactly, but we can have very good approach of it, especially if you look at my presentation. I make a virtual SEA model of the junction using RBE2 element, so finite element modeling of the junction. and compare the prediction from my small analytical model, and you see 1 or 2 dB maximum in terms of coupling loss factor from the finite element result, which is quite a good statistical modeling of the junction. So obviously the construction of the double glazing could be characterized with more measurement. But it means, in our case, that the only measurement we need is a transmission loss. And all the rest of the parameter could be default value. And we know that if really we are keen to being on the safe side, we can just add some measurement of the panel damping, and only with this property plus some thinking about the coupling loss factor between the two plates, or even a measurement of it, we can really have a perfect model for transmission loss at a very low cost. To conclude, our model is working quite efficiently, give very accurate data on compared to test, and explain how the system is behaving. So we know now if the system is mass dominated, we have to change the mass, or to change the data, or damping dominated. And it's a beauty of statistical energy analysis. So thank you very much to attend this presentation, and I will stop here.